Earlier, we studied the fundamental theorem of arithmetic, or how every integer can be written as a product of prime numbers in an essentially unique manner. So now I'm going to see how we can extend these results in arbitrary commutative integral domains. So let R be a commutative integral domain. And we want an analog of the notion of a prime. One way to generalize a prime number is the notion of an irreducible element. An element x belongs to R is said to be irreducible if whenever x equals AB, either A is a unit or B is a unit. So prime numbers are obviously irreducible. If you try to write them as a product of two integers, then one of those integers must be a unit. Okay, now let's try to see how we can take an element x of R and then try to, if it's not irreducible, we can write it as a product of two elements, neither of which are units. So if I have an element x, if it's irreducible, well, then it's irreducible. Otherwise I can try to write it as a product of two elements, x1 and x2. Now it could happen that both x1 and x2 are irreducible, in which case we have factored x into irreducibles. Otherwise, at least one of these would not be irreducible, or maybe both are not irreducible. So suppose x1 is not irreducible, then I can try to factor that further into x11 and x12. And maybe, x2 is irreducible. Then I leave it there. If not, I will also extend this branch of this tree. And let's say x11 is irreducible, but x12 is not, then I can write it as x121, x122, and so on. Now, if I do this, there's either one of two outcomes will happen. Either the process ends. So for example, if this process has ended at this stage, that is all these elements x11, x12, x121, x122, x2 are irreducible, then x has been written as a product x11, x12, x121, x122, x2. Okay, so and we have written x as a product of irreducibles, or the process continues indefinitely. Which means that at least one path down this tree will continue to branch indefinitely. So in that case, we'll have x is, I'll write down the element which is not irreducible, the branch which is not irreducible. The first time I'll call that A1, and the other branch I'll call x1. Now a1 is not irreducible, maybe x1 is also not irreducible, but this is the one I'll choose to factor further. And so then this will become a2 x2 x1, and again this one is not irreducible, then we'll get a3 x3 x2 x1 and so on. So in this example I'd start with x1 x2, so a1 would be x1 and x2 would actually be a1 and x2 would actually be x1, and then and so on, and none of these guys are units. Okay, now let's look at the ideals generated by these elements. So we have the ideal generated by x, and that is certainly contained in the ideal generated by a1, right? And cannot be equal because x1 is also not a unit. So this is a strictly larger ideal, and this is contained in the ideal generated by a2, and this is contained in the ideal generated by a3, and so on. What we get is an increasing, what we call a chain of ideals. I1 contained in I2, contained in I3, contained in I4, and so on. Increasing, and it's an infinite chain, and it's a strictly increasing infinite chain. Okay, now the fact is that this kind of thing does not happen in most rings that we come across in number theory or commuted in algebraic geometry. So this condition was made somewhat abstract by Emmy Noether, who may be considered the mother of ring theory. She was one of the pioneers in abstracting properties of rings, and she came up with this condition called the ascending chain condition on a ring. And the ascending chain condition, or it's now called the Noetherian condition in her honor, R is said to be a Noetherian ring if basically this kind of thing of having an strictly increasing infinite chain of ideals cannot happen. If whenever we have ideals I1 contained in I2, contained in I3, then I, which I defined to be the union is equal to ik for some k. So whenever we have an increasing chain of ideals, it must stabilize at some point. So you cannot have this strictly increasing infinite chain of ideals. Okay, this is the Noetherian condition. It's named after Emmy Noether. Okay, so what we've seen now is the following theorem. If R is a commutative integral domain, that is also Noetherian, then every element X belongs to R admits a decomposition X equals P1, P2, Pk, where P1, P2, Pk are irreducible elements. A principal ideal domain is an integral domain where every ideal is generated by a single element. Okay, we've already seen examples of principal ideal domains: the ring of all integers, the ring of all polynomials, and more generally any Euclidean domain is a principal ideal domain. Let me just write this down for you. An integral domain, a commutative integral domain, R is called a principal ideal domain. And this is usually abbreviated to PID if every ideal I of R is of the form it's singly generated, it's generated by a single element of A for some A in R. Okay, and as I just said, all Euclidean domains are principal ideal domains. Now, one very nice property of principal ideal domains is that they are Noetherian. Every principal ideal domain is Noetherian. Proof is very beautiful. So the proof goes like this. So suppose you have a chain of ideals. Is a chain of ideals in R. Let I be the union of all these ideals. Union n goes from 1 to infinity, in. Okay, then I claim that I itself is an ideal. Because if A belongs to I, then A belongs to ik for some k. And therefore AR belongs to ik for all R in R, which implies that AR is also in I for all R in R. Okay, therefore I satisfies the condition of being an ideal. But I is an ideal in R, and every ideal in R is principal. So I itself is generated by some element. Let's call it A0. Okay, and A0, well, A0 is in I, which means that A0 is in ik for some k greater than or equal to 1, which means that ik is equal to I, because A0 is in ik and A0 generates all of I. So certainly ik is equal to I, and this proves the theorem. So it's a very simple proof and just comes from the fact that an infinite union of a chain of the union of an infinite chain of ideals is again an ideal. Okay, so what we can say from this and what we discussed earlier, corollary, that every element in a principal ideal domain can be written as a product of irreducible elements. We have seen that every element in a principal ideal domain can be written as a product of irreducible elements. The question remains whether such a factorization is essentially unique or not. It turns out that the answer to this is yes. So every principal ideal domain has the property that every element can be written as a product of irreducible elements, and this factorization is essentially unique. If R is a PID, in other words, it's a commutative integral domain in which every ideal is principal, then every x in R can be written as x equals p1, p2, pk, where pi are irreducible. The uniqueness needs to be formulated a little more carefully. There are units, there could be a lot of units in a general PID. For example, in the ring of polynomials over a field, every non-zero element of the field is a unit. In the integers, only plus and minus 1 are units, and so usually when we state the fundamental theorem of arithmetic, we restrict ourselves to positive integers and we actually get uniqueness. So, so let me state uniqueness a little more carefully. This decomposition is unique in the sense that if x equals p1, p2, pk is equal to q1, q2, ql are two such decompositions, then k equals L, and the q1, q2, ql can be reordered we can write qi equals pi times ui for some units u1, u2, uk of R. So the factorization is unique up to multiplication by units. Okay, we've already seen the existence of the factorization. What we need to check now is the uniqueness. Now the proof of uniqueness is very similar to the proof of uniqueness that I did for integers, and so I'm just going to tell you one or two key steps in that proof which need to be generalized from integers to general principal ideal domains. So the key property that you need to generalize is the following. So theorem: if R is a PID and you have some element m in R and p in R where p is irreducible, then the ideal generated by m and p, well, this is going to be a principal ideal. The question is, what is it? This is the ideal generated by p if p divides m, and if p doesn't divide m, then this is the ideal generated by 1, which is equal to R otherwise. And the proof goes as follows. Well, so we know that the ideal generated by MP is equal is a principal ideal. So it's generated by some element Q, say. Okay. So what this means is that P is equal to Q times something, because P lies in the ideal generated by Q. So P is Q times some element U. So now there are two cases. Case 1, if Q is a unit. Okay, if Q is a unit, then Q is the ideal generated by Q is the same as the ideal generated by 1, and that is R. So we are in the second case. Case 2, well, remember that P is Q times U and P is irreducible. So if Q is not a unit, then U must be a unit. Then we know that Q is QU, which is P. And so we are in the first case. Okay. Now if you take this theorem here and go back to the proof of the fundamental theorem of arithmetic that I did a few lectures ago, you will be able to work out all the steps exactly as it was there and complete the proof. This is something you should all try to do.